Okay, let's jump right into this explainer and look at the fundamental problem of how software code actually interacts with the physical world. If you've ever written a line of code, you know it lives in this purely digital, theoretical space. But the whole point of the Internet of Things is making that code physically do something out there in reality. So today, we're unpacking Chapter 5, Embedded Programming. Think of this as the ultimate blueprint of the IoT nervous system. We've got a great roadmap ahead. We're going to explore the 4 specific bridges that cross the digital-physical divide. We'll start with the isolated brain, move into binary senses and actions, digitize the continuous world, check out the PWM illusion, and finally, orchestrate a complete smart agriculture system. All right, Section 1, the isolated brain and a processor's limitations. To really appreciate embedded programming, we first have to understand the inherent restrictions of a bare computer chip. What's really fascinating here is the concept of a super powerful processor that is, on its own, completely isolated from reality. It's got processing units, memory registers, all this logic, but it's literally trapped in a silicon box. Unless we build a bridge, none of those physical inputs or outputs mean absolutely anything to the hardware inside. To put it bluntly, and I love this description, a microcontroller in isolation is deaf, blind, and paralyzed. Without embedded programming, it has absolutely no way to translate physical phenomena, like heat or motion, into electrical signals. And it can't translate electrical signals back into physical action. That translation layer, that's the entire core of what we are unpacking today. Moving on to Section 2, Binary Senses and Actions. Let's start building our bridge by looking at the sharp contrast between the absolute digital world and the messy spectrum of reality. So the crucial point to remember is that digital code deals purely in absolute on or off states, right? But the physical world exists on an infinite, continuous analog spectrum. Digital is binary. It relies entirely on Boolean logic, true or false, 1 or 0. Meanwhile, things like temperatures rise gradually. They don't just snap from freezing to boiling in a microsecond. To bridge these two totally different realities, we have to establish some hard rules for translation. Our first modality is digital output. This commands the microcontroller to push a fixed, absolute voltage to a specific pin. Think of this as the binary action. It's the most fundamental, basic way a chip can assert its will onto the physical world. This is a literal 1, 2, 3-step process of how a Boolean true in your software instantly becomes a physical action in hardware. Step 1. Your code executes a value of 1. Step 2. The microcontroller immediately responds by pushing a logic high, usually 3.3 or 5 volts, straight out through a pin. Step 3, that sudden voltage hits an actuator, triggering a physical valve to open. Boom. Code becomes action instantly. Now let's flip it. Our second modality is digital input, which allows us to monitor a pin so we can translate physical connections into actionable code. This is the binary sense. It's exactly how the brain detects when a definitive yes or no event has occurred out in the real world. Notice the reverse flow happening here. Step 1, a physical magnetic door contact separates. Because of that, Step 2, the electrical circuit is broken and the voltage instantly drops to 0. Finally, in Step 3, the code that's constantly monitoring that pin evaluates the sudden voltage drop as a 0 or false. Physical change just became actionable code, ready to trigger an alarm. But look, the physical world isn't just a bunch of binary switches, is it? Let's jump to Section 3, digitizing the continuous world. We need to figure out how to sense continuous spectrums. This brings us to our third modality, analog inputs. These are absolutely essential because things like temperature, light intensity, and soil moisture exist on infinite curves. They aren't just dry or wet. They exist at a very specific percentage of hydration, and we need our microcontroller to understand those fine nuances. But wait, this presents a massive logical dilemma. How on earth does a digital processor, a thing that only understands ones and zeros, comprehend an infinite, non-binary spectrum? It structurally cannot handle an infinite range of decimal numbers coming straight from a physical sensor. Well, the brilliant solution is analog to digital conversion, or ADC. This literally pixelates the physical world into a staircase. It takes a smooth, continuous analog voltage wave from a sensor and snaps it down to the nearest available discrete step, often one of 1,024 steps. So a soil moisture level doesn't come into your code as infinitely wet. It comes in as exactly the number 742. We've successfully translated infinity into a format the digital brain can finally digest. Section 4, the PWM continuous illusion.
Now that we can read analog signals, we need a way to send continuous outputs back into the real world.
Our fourth modality is analog output. Writing a simulated continuous voltage allows us to do incredibly useful things, like smoothly dimming lights or controlling the precise speed of motors. But doing this from a purely digital chip, it's actually an incredible trick. You see, microcontrollers cannot output varying continuous voltages. Their pins are either entirely on, pushing full voltage, or entirely off. So they use pulse width modulation, or PWM, to rapidly flip digital pins on and off. It creates an illusion, exactly like flipping static images in a flipbook creates the illusion of smooth motion. It pulses that full voltage so incredibly fast that the physical component experiences it as a smooth, partial voltage.
Time translates directly to power here. The percentage of time the signal remains high is known as the duty cycle, and that dictates the average voltage delivered. So at a 50% duty cycle, the signal is on half the time and off half the time. The result? An LED appears exactly half as bright. It's just an ingenious illusion.
All right, Section 5, Smart Agriculture Orchestration. Let's see how all of this builds into a complete real-world symphony by combining all four of these isolated bridges. Take a look at this taxonomy. It perfectly categorizes our physical farm components into the four embedded programming modalities we just analyzed. We have digital inputs like door switches and analog inputs like soil moisture probes. Over on the action side, we've got digital outputs like simple water pump relays and analog outputs for things like variable speed DC motor fans. Every single physical component has its designated digital translation layer.
In our smart agriculture setup, the microcontroller acts as the grand conductor. It's simultaneously reading a discrete door switch and a continuous moisture probe, while actively controlling a binary water pump and a variable speed ventilation fan. It handles all four modalities at once, without missing a single beat. When you look at the actual MicroPython logic, you can clearly see how a single while-true loop constantly evaluates these digital and analog states to maintain perfect environmental harmony. It checks if the door is open. It checks the exact ADC value of the moisture. Then it triggers the necessary actions, flipping digital pins entirely high or adjusting the precise PWM duty cycle to literally orchestrate reality. And there it is, the blueprint is complete. We now have the full set of programmatic tools to bridge isolated software logic with the dynamic physical world. By mastering binary senses, binary actions, continuous sensing through ADC, and continuous actions through the PWM illusion, the entire Internet of Things becomes possible. So, what's the big takeaway from this explainer? It's that absolutely every IoT system relies on this exact matrix. So I want you to look around. Look at the smart thermostat or the automated lights in your own home. Which modality is doing the heavy lifting right now? Think about the continuous illusions and digital translations happening right in your living room as we speak. Thanks for exploring the foundation of embedded programming with me. Keep looking for those real-world connections, and I'll catch you next time.